Yes, I know it's weird to come into a video and see stuff. Don't look at the button, don't look at your scroll bar, your video progress bar to see, well, maybe I came in the middle of the video. No, this is just the leftovers from the last video. Now, the reason I left it up there is because there's a lot of what I want to talk about in this video already on this screen, on this light board. So, what are we talking about? Well, remember, we have worked our way up through the memory hierarchy till we get to the point where we're talking about registers. Registers, that's small, very small. In the case of the ARM processor, 16 memory locations. Very small memory at the top of the memory hierarchy. Now, I want to talk about the different types of registers there are. There are actually three kinds of registers. There are data registers. Guess what those hold? Well, those hold data. The numbers that we're processing, so the values that we bring in from our variables that are stored out in memory, the numbers we bring in, and we do the processing on them using the ALU and then store them back out. That's one kind of register. There's also another kind of register called a flag register, or flags. We are going to talk about that in a future video, but the one we're going to start talking about now is pointer registers. These registers, there are many registers that contain addresses, and I could probably call that this address register. So registers can contain data, flags, or addresses. Some registers are called index registers that also store addresses. But there are a couple of these address-containing registers that I want to talk about. And so if you go all the way down, and I know I'm kind of biased towards ARM processors. I don't mean to be. It's just what I have more experience with. The last register, the 16th register in this list of registers, is actually called a program counter. In the Intel processor, it's called an instruction pointer. And in fact, Intel's description of this register name probably makes a little bit more sense than program counter. Instruction pointer. It points to an instruction. Specifically, it contains the address, and I started to write down points here. Let's just go ahead and stay away from the language of like C and C++ and so forth. It contains the address of the next instruction to execute. All right, so there you go. There's a definition of the program counter or instruction pointer. Same thing, just a different processor we're talking about. Okay. Now, the reason I left this up here is because it's tightly coupled to what goes on here between the instruction decoder and the bus interface unit. Remember, our first instruction that we were executing was these four addresses right here. It was stored. Remember, the data structure alignment said that all 32-bit addresses, all 32-bit instructions, all have an address that ends in 0, 4, 8, or C. Those are the addresses. And we also have it stored in Little Endian so that the most significant byte is the last one of the four addresses, and then we have the next and the next into the least significant one, okay? So there's our instruction, the instruction we want to execute. Now, the reason we need a program counter is, well, we need to keep track of where we are in our code. So whenever we came into this code, the program counter right here, it contained 8000 hex. It contained that in this register. And in the case of the ARM processor, it's this last register, which is identified as R15. Now, it's pointing to this instruction right now. So the value in here is 8000. Now, the instruction decoder goes and looks at the program counter. 8,000. That's what's contained in it. And so it knows to tell the bus interface unit, go grab the instruction at 8,000. All right. Now, once it's grabbed the instruction at 8,000, I can't leave this at 8,000 or else we'll just keep executing that instruction over and over and over again. What does the instruction decoder need to do now? Well, the instruction decoder, because of the architecture of the ARM processor and many other processors that use fixed width instructions, in other words, instructions that are always the same size, it'll just simply add 4 to it so that we're automatically pointing to the next instruction. And so this now contains 8,004. 8,004. After the execution of this instruction, the instruction decoder goes to the program counter, 8,004. 8,004, it just simply grabs the next instruction. Now, this works really well if all the instructions are one right after the other, after the other, after the other, right? Yes. Sometimes, however, we have something called a branch, a jump. Something that takes us from one part of our code and jumps over instructions, or maybe even jumps back. Think about a loop. In a loop, when you get to the bottom of the loop, if you need to execute the loop again, you go back up to the top, right? And so you keep executing, and you have to do that jump or that branch. How do we do a branch? Well, it's real easy. If you do a branch, it may just simply say branch, and in the assembly language, it may be a simple instruction like BRA. And maybe it'll give a label, right? So some sort of a label, some name that we're branching to. And that corresponds to an address. So you know how that instruction works? Just simply loads a new value in R15, or the program counter, or the instruction pointer. Just loads the address of that guy right in there. That way, we have this ability to know always what the next instruction is to execute, and to even change what the next instruction we're going to execute is. It gives us a lot of power. Now in the next lesson, we're actually going to jump up here. There's another one here. We're going to look at R13. This guy, I will erase this for the next lesson. This guy, R13, that also contains a register. It is also a pointer register. It's called a stack pointer. We'll talk about that in the next lesson.